this one. All right. So last time, if you remember, we were talking about uh, backend, right? And we kind of covered most of things, right? The last thing we want to talk about is this part here, the load store units. Okay. So what is a load store unit? Load store units is essentially the bridge between the memory and the processor, right? So that, since we need to constantly read and write data from the processor, we need what we call a load store unit for various different reasons. There are several important issues that we're going to talk about, and load store units are basically to fix those issues. Remember, when we are talking about memory here, we're mainly talking about sending and receiving data. Because remember that we had our instruction cache and instruction was kind of handled by the fetch unit. We're talking here about the data. And if you remember, I told you that essentially we can have two separate memories, one for data and one for instruction. And there are architectures that kind of have separate memories. But in reality, these two memories are essentially part of the same unified memory, okay? And we usually have these sections, the data section, the instruction section, the cache sections, sorry, not the cache, the stack section, the heap section, and so on and so forth. So when we are saying data, we are essentially saying that we're talking to that particular section in the code, which is, sequence of addresses. But there is no fundamentally different way of handling instruction versus data, okay? But when we say, the load store unit, and generally when we have this pipeline here, here we are talking about data only. The instruction is here, okay? So the instruction part is here, but these two are physically part of the same physical component, okay? So just notice the difference. All right, so what are the problems that we are worried about when we are talking to the memory for an out of order execution unit? And how should we solve them? That's the story of LSU load store units. So there are these kind of 5 things that we need to kind of take care of, okay? The big thing is the memory data dependence. And I'm going to talk about what is that and why is it different than other data dependence. Then once you have the data dependence, then we have 2 things. One is what we call load skipping or load bypassing, which one load can be issued out of order from the other. And then the second thing is that we need to have a mechanism for what we call a load forwarding, which, younger loads receive the data from the older loads. Similar story that we had for registers. And this load is actually load store forwarding. So sometimes it actually can come from the store. Then we have what we call disambiguation or memory disambiguation. And we're going to talk about an optimization that we do in order to do this speculatively in order to get it faster. And lastly, we need to talk about the memory bottleneck as a whole. And this is kind of the story that we're going to talk about next lecture when we are talking about the cache designs and all those things. Okay. So let's just start one by one. Let's just talk about the memory dependence. So think about scenarios like this. That's very similar to the way that we had dependency between 2 variables, 2 registers. You can have same dependency between addresses in memory. So if I have something like store store X, right? This is what we call write after write. And of course, if I kind of move this out of order, then the value of X, the value that we're going to store in the memory would be different, would be wrong. So we need to make sure that we kind of maintain this ordering. Otherwise, we're going to have write after write, dependency hazard. In CPUs, we fix this for registers by doing the renaming. We're going to see how we can fix this for memory. Similar story for var and raw. So if you have a load after store, right, we're going to have write after read hazard. Or if you do the read after write hazard, these are all problems that if we change the ordering, we're going to have those problems, right? So in terms of this ordering, so the first thing that comes into the mind is, okay, let's maintain all these orders, right? If I maintain all these orders, then I don't have data dependency. So essentially, when it comes to the memory, we can do everything in order, right? And that will instantly save all of the problem that we have. But things that we have learned so far is that we are not interested in doing things in order. The main reason is the performance issues. So essentially, there are two things that we kind of like you can think about, right? So from the perspective of the load might wonder that why do I need to wait for another loads or another stores if the other loads or stores are not even relevant to me, right? So like obviously this case is an important case, but what if it's like load Y, right? Or for example, here is load Y. We don't need to wait for anyone because this is an independent memory instruction. It can be in any order that you want. Same way that we reordered independent instructions, we should be able to reorder load instructions. The reason that this is very important for us is, for example, if this one is a cache miss, then everybody has to kind of wait for this data to come, right? So everybody has to kind of waste a lot of cycles. Versus if I could like issue this here, then while this one is waiting, then I can do lots of good stuff, right? So it's the same story that we did for the out of order execution. And the same thing for a store, right? So the store would wonder that why should I wait for other stores or other loads when they're completely irrelevant to me, right? So the kind of like, similar, as I said, similar to most of the things that we discussed so far, the idea is that we need to reorder, being able to reorder loads and stores the relative to each other in order to achieve performance. Otherwise, we're kind of paying the penalty of our cache, subsystem. Okay. But then the dilemma is if I do reordering, I'm going to have this problem, right? So I need to kind of come up with a method that can efficiently kind of fix this memory reordering problem by giving us the capability of doing the reorder. Okay. And then if you think about this, the possibilities that you usually like, there are four possibilities. There's what we call a total ordering, which means that, oh, okay, everything has to be in order. Then we have what we call partial ordering, which, we say that essentially all the stores are in order, but loads are out of order as long as previous stores has computed their addresses. So once we know the address of the store, then we are allowed to move loads around. Stores still needs to be in order. Then we have load ordering and store ordering. And this is essentially the execution between load and stores are out of order, but all the loads are in order among themselves and all the stores are in order among themselves. So you can kind of like think about like, I'm free between loads and free between stores, but within each group, I need to do it in order. And finally, we can have what we call store ordering, which again, stores execute in order, but just loads are completely out of order, right? So we don't care when each load happens. We may not even have the address of a store, and we can issue those, right? So this is what's called store ordering, okay? And these are, and then if you look at the middle column, is like talking about speculative, and then of course this one needs to be speculative because since we don't know the address of store, then there might be a raw data hazard that we are kind of skipping. So we need to kind of like predict that whether this would be a raw data hazard or not, and based on that, make a decision. Okay. So let's talk about the problems, right? So what would these things, how these things cause a problem, and how do we fix it? So we're going to have the main issue that we are thinking about to fix this problem is understanding that memory is fundamentally different than registers because we have what we call ambiguation, okay? And as a result, we need to do disambiguation. So what is an ambiguation? Think about this code here that we have two important registers here. We have R7 here that is being kind of like, stored into. And then we have also like register R1, which is load from, okay? And now if you think about R7 and R1, the main thing here is if R1 and R7 are different from each other, right? Then we don't have any issue because like, this part is completely separate from this part, right? And R7 and R1 are two just different registers, two different addresses. This part runs and store the data into R7. This part does various things and load the data from R1, right? So everything is great. But the problem is that if R7 and R1 are indeed the same, what will happen is that the address that we are storing to, so this is the store to address X, and this is load to address Y, right? So add load from address Y. But if R1 and R7 are the same, then X and Y becomes the same. So now the order matters a lot, because if I load R1 here, I'm gonna load an old value, versus if I load this after this is stored, then I'm gonna get the updated value because of these kind of add and subtract and all those tricks that we did. Okay. So completely true outcome from this system, especially for R8, depending on whether R1 and R7 is the same. And now the problem, the ambiguity here is you cannot tell by looking at this code and saying that, oh, these two are the same or are not the same. Depends on the other values, depending on the dynamic change of the system, right? As a result, there's no way that compiler or renaming logic could fix this issue, okay? The only way that we can fix this issue is the time that we actually compute the address. Only at that time we know whether R1 and R7 are the same thing or not. Okay, and that's the ambiguity that we are talking. Okay, so you might wonder that why we don't have this ambiguity, in non-memory instructions, because in non-memory instructions the operands are absolute. Like you have R1 and R2 and R3, or X1 or X2 and X3, so you know exactly the address. The address is basically the index of that register, right? So you know that this is X1, this is X2, so you know beforehand that whether these two are the same or not. Okay, but in memory, R1 is not pointing to one particular address. Could be to any address. Any number between 0 to 2 to the power 31 minus 1 is essentially a possibility for the address. So no way that knowing this, what's the difference, okay? So as a result, in order to kind of determine that whether we can reorder these things the way that we want, we kind of need to disambiguate these addresses, right? Otherwise, we might get lucky and not get into the scenario like this. But if we get this to scenario like this is the correctness issue again, it will result in your system to actually generate a different number, and this is not acceptable. This is not like a performance issue. This is a correctness issue, and we have to fix it, right? So how do we do the disambiguation? So first of all, a little bit of terminologies. So we have this thing called memory aliasing. And memory aliasing is exactly this problem that I explained. When two addresses are mapped into, when two variables maps into the same address, we call that there is an aliasing between these two, okay? And memory disambiguation is the process of determining whether these two addresses are the same or not, right? So determining whether we have aliasing or not, that's the process of disambiguation, okay? So how do you think we should fix this issue, and what's the memory dependence detection should look like? Yeah.
Read the value of the memory and see if they equal to each other.
Yeah, check the addresses, right? Like have a mechanism to check these addresses and then see whether these two addresses are. So before actually issuing them into the memory system, we need to kind of intercept this at some level, see the addresses that are coming, and see whether these two addresses are same or not, right? So instead of like directly going into the memory, we need to kind of like, compute what we call the effective address, the actual address, and then compare these two addresses at runtime, and then see whether these two addresses are the same or not, okay? One big problem is that, comparing addresses require very wide comparisons, right? Because, these addresses 32-bit numbers, so there are, difficulty of doing comparison, but anyway, we need to do the comparison, right? So there are two steps that we need to do, right? The first is detection, which is comparing the addresses. And the second thing is, okay, now let's say we have detected that, okay, there is dependency. If there is no dependency, there's nothing to do. We just let them go, right? But now if there is dependency, now the question is, what should we do? And the solution is forwarding, right? So we should forward we should find the most recent store and forward it from there, right? So that's kind of like what we need to do in order to fix this forwarding. Okay. So how do we do? Excuse me. How do we do that? We're gonna use this ls load store unit, as I said. We're gonna have a queue within this ls unit called ls queues. And then what this ls queue does is that every load and store that needs to go to the memory, the processor push this into a queue. Okay. And then what happens is that for a load, we're gonna look into this queue and see whether there are previous addresses that happens to have the same address with this load, okay? If there is one, then we're gonna kind of forward the value from that queue instead of going to the memory. This way, as long as we push things into this queue, as long as we check this queue in program order, then we are good to go and we can actually kind of like, do this things the way that we want to do, okay? So at that point, there is one big question, and that is that, what if you actually already reordered this instruction? Like, the load is before the store, and you haven't even seen the store, right? So this is like the problem that we need to fix at this point. So first of all, let's assume that, store happens before load. So we actually have the ordering between load and stores. So what will happen is, all we need to do is that we check the matching. If we see a match, we forward. If we don't see a match, we skip, right? So as simple as that. We have a queue that essentially everybody kind of like, push things into this queue, the loads and stores. And if the new load comes, they will check the latest stores here, and then they find the latest store, and then the value will be forwarded from the store to the load, right? Or for example, if there are multiple stores, then we're gonna basically make sure that the ordering is right, so that the older stores run first and the newer stores run second. So the ordering can happen within the load store queue. The forwarding can also happen within the load store queue. There's still one problem that we don't know how to solve, and that is, if by the time that we are doing the load, we still haven't seen the store, what should we do? And I'm going to talk about that later. Okay. But for now, let's assume that the ordering is correct. So first of all, the first question is, if things are actually in order, then would this be fast enough for us or not? Like, if we don't assume that, oh, the load is not before the store, is this fast enough? And the main reason for that is, what if we don't know the address, right? So if we don't know whether the address of the store is known at the time that we issue the load, then we have to say that, okay, the load has to wait, right? Otherwise, I'm risking the fact that there might be some disambiguation, might be some aliasing, and might have some issue. Okay. So in order to make this faster, we need to kind of come up with the scenario that we can issue the load even before knowing the address of the store. Okay. And this is what we call speculative disambiguation. Okay. We're gonna guess whether or not there is the dependency between the load and store. Okay. So the idea is this, that if aliasing is rare, that is like, it's very unlikely that two addresses are actually from the same memory, then we can always bypass, right? So we can always say that, oh, you know what? Load is not going to be dependent on the store. You are good to go. Okay. And then of course we need a mechanism for fixing this issue and kind of going back. And then in order to do that, we will have this kind of like this method of, if you remember, we had a method difference between commit and complete. So for the load, we can always issue the loads whenever we want. Okay, we reading it from the memory, no problem with issuing the load as much as you want, even if you're reading an incorrect value. What we need to do is essentially during the commit stage of the stores, make sure that the addresses was the same addresses that we thought. If the addresses were not the same addresses, as in like there were no matching loads, then we are good to go. There is nothing need to be done. If we see that, oh, we actually did an incorrect load speculation, then we need to replay and start from the incorrect load, okay? So here's what happens, right? So you have sequence of some loads and some stores, okay? So what will happen is, so first of all, this load, for example, just go. This store goes into the queue. So all of them goes into queue. So this one goes into queue. Then let's say, for example, at some point we have a load, okay? So what we would do is we are saying that, okay, this load might or may not depend on this store. We don't know, okay? What we're going to do is that we're going to say that, you know what, you go. We think that there is no dependency. So this one will go into the main memory and bring the data, okay? Again, nothing bad happens in our system because we're just reading some value. And then we continue our life. At some point, this is store going to reach into the commit stage, okay? At the commit, for sure we know the address, okay? So now we're going to check that whether there are load addresses, future load addresses that had a dependency with this address. If we didn't find anything, then it means that our speculation was correct. Nothing to be worried about. If we find that, oh, you know what, this address was indeed this address, it means that this load read an incorrect value. As a result, we need to replay this roll. So we need to roll back and go to the wherever that load address was, and we need to restart from that one. Okay. And again, given that we commit in order, remember we always commit in order, we are guaranteeing that at this point the ordering is correct, right? Future instructions we don't know, but anything before this we do know because we commit in order. So as long as we follow the commitment in order, we are good to go. Does that make sense? Awesome. So this is kind of like, straightforward approach. And this is usually what happens in most cases. The other question might be, oh, okay, what if the aliasing, do I have this? Yeah, and then as I said, what if it's not? And then now the question is, what if the aliasing is actually happening more often, right? In that case, again, similar to the way that we described many times in this class, you can have like a pattern history table kind of, table that we had in BTB that kind of predicts that for a given address, have we seen aliasing before or not? If we do, then we can delay the load, right? Think that, oh, okay, we predict that there is an aliasing. So very likely this load going to be kind of like, repeated. So let's not actually issue this load. Let's wait a little bit more for the store address to be known. And then we can then decide whether or not we want to do that, okay? And then there are pairs that you need to also discuss. I think we can skip this, but generally let's just focus on this one where we're gonna have a load and store pair. And if you think that, oh, there is a good chance that this load is gonna be dependent, then we don't issue this load. Okay. So here's how the load store queue works in Boom. So we have a store queue and we have a load queue. The core is essentially at the decode stage, okay? At the decode stage, we know the load and store, okay? So we put it into the load queue and store queue. And remember, the decode stage was in order. So we kind of guaranteeing to make sure that, our load store queues are populated in order, right? And then what we have is that we have this controller that kind of takes these entries and then make a decision about what should we do. So the controller essentially go to this searcher, which all the store queues and load queue entries goes. And here that's when we see that whether there's a match or there is no match. If there is a match, then we need to do the forwarding. If there is a match, we also need to kind of like either kill and then go back and do all those kind of like recovery stuff. And then as you can see, essentially there are kind of three stages that load store queues are involved. So load store queues is not just for the decoding. During the decoding, we essentially push things into the queue. During the execution, we know now the outcome, the address of the table. And during the memory stage, that's when we actually issue things or recover things if need be, right? That's kind of the story of this. And then, of course, at the write back stage, that's when we are actually kind of actually issuing the actual load to the memory. Okay, if you want to really store things into the memory, that's when we're actually issuing it to the memory. Okay. There are a whole bunch of like different units inside, like each of this controller. The controllers actually have different stages. I think you cannot see this very well because it took a screenshot, but things like, oh, this the address is virtual. Is it the address executed? Is this order failed? All those things. And by the way, the thing that we didn't really discuss in the class is addresses or virtual addresses, and then we also have physical addresses, so you need some form of translation. But for now, just assume that everything is physical. Essentially, what you store in your queues are physical addresses. So you need a translation between virtual to physical. If you don't know what is a virtual address is, don't worry about it. That's something for another class. Okay. Questions? Good. Yeah.
So you have a store and then followed by a load.
Uh-huh.
How long does it take for the store to reach the commit stage? Like how many more instructions can happen after the load?
How many more instructions can happen after a load?
So
Depending, I don't know about Boom, but it depending on how like long your execution pipeline is. Some of them are like multiple cycles, like 4 cycles. For example, for Boom, it was 4 cycles. So essentially, you could technically issue 4 loads after one store using Boom core. And then also think about that you have multiple of these execution units. So each one could potentially take one. So 4 times the number of kind of units that you have.
So here's my question. If you have a store and a load and you speculatively decide that they're not the same address, except what they actually are. So by the time you found out your load already loaded wrong values, and if you loaded the wrong value and you have a bunch of calculations that follow, the subsequent instructions could have a division by 0 or some kind of weird error. How would you recover from that?
So again, so once you detect that you made a mistake, you start from that load and you start everything from there.
What if before that there's already a division by 0? What would the system react?
Well, you shouldn't have a division by 0 necessarily. So I mean, it's again, if you have a division by 0, you will have an exception being raised, okay? And the exception also will go into some queue to be handled. And again, since the exception that caused by misambiguation or misspeculation is prior to that exception, you first do the misspeculation for that. So what you're saying is that if I have kind of like misspeculation here and a bunch of weird exceptions here, what will happen? Same thing with the way that we handle instructions. We start with the age. So essentially there is a queue for exception as well. We handle this first. And then if need be, we handle the rest. But once we handle this, then we see that actually all of them are not. But you're actually in the very right. You're actually in the right track. You're actually what you're saying is exactly how meltdown attack works, and we're going to talk about it actually next week. So the way that meltdown, now that we discussed this, the way that meltdown works is, imagine you have a speculation here, and you create an exception here. Okay, so for example, you access an out of bound address, the address that does not belong to you. Okay, in regular system, if you try to access something, the operating system will block it and creates an exception. You will have core dump or whatever, the way that you capture the exception. So it will be blocked and never be executed. In this case, though, if I have this kind of memory here and I have another memory access here, I'm going to issue both of them first. I'm going to load both of them, okay? And later on, I'm going to see that, oh, you know what? I actually did a misspecification. And you see that there's a tiny exception going on here as well. But as long as I'm doing the misspecification here, I don't need to even care about that exception. So I'm going to just ignore that exception as well. So I never will notice that, oh, somebody actually read something that they were not supposed to. And the beauty of this is actually this load has been issued, which means that the data has been brought to the cache and has been brought to the CPU. So now if the adversary can actually somehow read that data, then it's a fair game for them, right? So that's the actual problem that we have in the system, actually. But if you think about it, you might say that, okay, then why don't we handle this exception? And you can. But the problem is that there are many, many instances. This is completely unnecessary, right? Because it's not even supposed to be executed. So there's no point of like even checking this, right? And it's also after the fact anyway. So this is not a good solution in order to fix this problem. But yeah, very good observation. Yeah.
How common is the wrong calculation in terms of this speculation compared to branch prediction?
I think it's much, much less wrong because the number of aliasing is much less. So it's like the number of branches is 20% of our program. The number of aliasing is very, very less because first of all, the number of loads and stores were less. And second, the number of stores and loads in the same address. So in terms of accuracy, I don't know, but maybe it's not as accurate as a branch predictor, but in terms of impact, significantly less. Yeah, so further more about Boom. So Boom is actually in order to kind of think about like which type of stores and loads can be reordered in Boom. Boom using this RV RISC-V WMO memory model, which means that writes the stores are write read constraints are relaxed, which means that reads can newer load can be executed before older stores. Okay, this is what we want in terms of performance. And of course, this means that we need to speculative, disambiguation. Read constraints are maintained. So loads as appear in the same order. And writes also appear in their same order. Okay, so this is what we call WMO. Let me see. Yeah, so and then per thread the reads can happen before writes. Essentially, that's the memory model that Boom has. So essentially, reads and writes can be reordered in Boom core. That's important things to remember. Okay. The last thing that we want to talk about to kind of finish the story of the backend is the write back and commit. Essentially, this is the step where we actually get the data and we know that we reach to the head of the ROB. Remember, we never write to the memory or register file unless we're absolutely sure that this instruction is going to be executed, which means that when it's reached to the head of the ROB, that's when the actual write back and commit happens, okay? Otherwise, things are kind of like stored in this temporary buffers into the register file, the dirty part of the register file, into the LSQ, into the dirty part of the rat and all those things. Once we clear that this instruction is going to be committed, then we're going to actually write it into the permanent part of the register file. Then we can actually issue it to the memory for being written and so on and so forth. Okay, so that's the write back is kind of like very straightforward. There's nothing specific about it. The only thing is that if you remember in our ROB we had that kind of head of the ROB, and then when we reach that head of the ROB, we're gonna write back everything in that row all together if you can. Okay. This is again one last time to show you the processor. As you can see, this is essentially the backend side of it, which do the reordering buffer, the allocation. Then we had the distributed scheduler, if you remember, and we had a register file when we did read after issue, right? So we issue things and then read it from the register files. Then we have a bunch of different execution units. You have ALU operation, floating points, memory, and so on and so forth. Then from the execution units, we connect things to the load store queues. Okay. So the store and loads, like, everything first goes into these queues. And of course, we have a forwarding from the stores to the loads if need be. So if there are future loads, once we detect the matching, we're going to forward it to the loads. And then from loads and from stores, then we can issue things to actual cache. This is the actual data cache that we have, and then we actually issue things into the cache. Okay. And then from the cache, we have multiple cache. For example, Boom has 2 caches, L1 cache and L2 cache. As you can see, L1 cache has distributed between L1 instruction cache and L1 data cache. So there's actually, these are 2 separate units. But the L2 is actually unified among both L1 and instruction and data. So there's one L2 cache, but there's one L1I and then L1D. To kind of give you a size, L1 data cache is usually 32 kilobytes, 8-byte set associative. L1I is also 32 kilobytes, 8-byte set associative. L2, since it's using different technology sometimes, it's much bigger, 512 kilobytes. Again, 8-byte set associative. And then you can potentially have L3 and so on here as well if you need to. So this would be a kind of off chip. So from L2, you're going to have an L3. And then from L3, you're going to have the DRAM basically at this point, right? And from DRAM, we can have a disk, which we're going to talk about next week. Okay? Make sense? Any questions? All right. So that's kind of it with the back end. Let's have a quick 5-minute break, and then we're going to start talking about the memory unit and the cache system. Continue. All right, so I'm going to briefly talk about memory subsystem. We have about like 45 minutes-ish. One big thing that I want to say is today's this module is mainly just quickly reviewing things that you probably know already. So we're going to talk about the structure of the cache, some optimizations. Next week, we're going to then actually talk about advanced topics and cache. So this is kind of like, if you've taken course with me, let me see. I don't have it here. This will be basically two lectures that I had there. I'm gonna actually link. I think I put the link somewhere. I don't know where it is. But if you want to if you had no idea about what the cache is and what's the structure of the cache, then you should watch those 2 lectures before watching this or looking at this in the class. How many of you don't know what a cache is or have no idea about a cache? How many of you don't know what is a set associative cache is? Okay. So pretty much most people know. I'm going to explain a little bit of that as well. But again, if you feel lost, go back and watch those and then come back and rewatch this, okay? All right. So we have this thing called memory hierarchy, and it kind of gave you a little bit of background of why we need this, and most of you already know why we need this. We essentially have the CPU at the top, and we need a lot of data and instruction to kind of being sent and received all the time. The problem with the memory is that we cannot yet figure out to have a big memory that is also very fast. As a result, we need to kind of do this trick of kind of gradually increasing the size of the memory and gradually increasing the delay. And by kind of intelligently move data around, then we can have the illusion that we have as fast of a memory as fast as M1, but as big as M3, right? That's kind of like the idea of memory hierarchy. Again, if someday the technology is advanced enough that we can have big memories that's as fast as as fast as CPUs, then the whole story of cache hierarchy is kind of gone, right? And then for those of you who are interested, there are a whole bunch of works in what we call in-memory computation, okay? In-memory computation idea is actually exactly this, that if I put the computation close to my memory, then I can send and receive data very, very fast, okay? And then this is kind of becoming reality because of these 3D memories, okay? 3D memories these days is, you can actually build memories on top of each other. And the nice and cool thing is that now you can put logic at the bottom. Okay, so you can actually literally build silicons that has the logic at the bottom and then has memories on top of each other. And now you have very, very fast access through this WIOS, this communication kind of like links. Then you can like read and write with high bandwidth and very low latency. And this is kind of the story of what we are envisioning our memory systems will be. And there are early version of this. It still hasn't been mass produced, but the future would be a future of 3D memories. Memory hierarchy won't go away completely, but hopefully the memory bottleneck will be solved by these new technologies. I'm going to talk a little bit about these at the end of this class in week 10. Okay, but now let's talk about more of like conventional systems, which we do have an L1 cache and an L2 cache and a DRAM and so on. This is all the systems that we have currently are like that. Okay. So the biggest problem for cache design is that we have limited space. We cannot store everything that we want. As a result, we need to be able to kind of find an intelligent way to do the data management, the data movement. We need to bring the data that we need the most, the closest to the processor, and then have a method of kind of like moving data away and bringing data back and so on and so forth. As a result, our cache is much smaller than memory. And of course, there will be units in the cache that are mapped to many memory lines in the main memory, because this is just a simple kind of mapping problem. The domain here is smaller than this domain, so there are lots of aliasing between these addresses. Okay, so the idea is that how should I find a systematic mechanism to know where each of these addresses should go into the cache? Okay, this is the kind of addressing or structure mechanism. The simplest one is what we call a direct map. Okay, so the direct map is that, think about the address. In this case, let's think that the address is just a 3-bit data. So basically all the possible numbers for the address is 000 all the way to 111. And then essentially, let's say the content is ABCD. So I'm just putting random content. So what will happen is that what we can say is that, let's say our cache has 4 elements. Okay, so we are basically trying to map an 8-element memory to a 4-element cache. As a result, each element will have at least 2 collision. Okay, so how do we do that? We basically can say that, okay, let's use the lower 2-bit, because this is 4 entries, so log of that means 2. So let's use 2 bits in order to address this memory. Okay, and this is how we're going to address it. In order to kind of distinguish then between this one and this one, because these two both map into this line, then we need to store the tag, and the tag would be basically the 2nd bit. Okay, so we store the tag, which in this case would be either 0 or 1. And of course, we need to store the data, the content itself. So we have what we call a tag store, which is just remembering the mapping. And then we have a fully content store, which is kind of a one-to-one mapping between the tag and data. Okay, basically here we are storing either A or E or B or F and so on and so forth. Okay, that's the story of a direct map cache. And the alternative to the direct map is, let's actually not have any index. Let's just do free for all kind of things. Let's do first come, first serve design, which we call fully associative, which means that all these lines could be mapped to any of these lines here. The way we're going to do it is that whichever is free, we're going to assign to it. Okay, either in a random fashion, in some other fashion that we're going to talk about later. But generally, we just assign things to the cache as things are coming. And then, of course, another problem is that once it gets full, we need another mechanism to kick things out and replace it with a new cache. And that's a separate story. But we call this fully associative. Okay. So now the question becomes, can I have, and then each one has advantages and disadvantages. The advantage of direct map is that it's very simple. Very quickly you can find where it needs to go. But it doesn't really utilize the entire, space of the cache, because imagine that all your addresses are like this, like everything AAA. So instead of like really, sorry, all the addresses starts with 0, 0. So instead of really utilizing the entire space of the cache, you are kind of saying that, oh, everybody has to just sit in this one first row. And then if somebody else comes, then given that, although there are more seats available in the class, they all needs to sit in just one row. So I'm limiting myself to utilize more space. Fully associative, on the other hand, is great for utilization because essentially you're saying that, oh, whenever there is a free space, we're going to assign it to someone. But search space in fully associative is much more complex because it needs more time to find that spot. Because direct map, you already know where you should go, versus fully associative, you need to search. Okay, so that's kind of like the motivation of finding something that's kind of a bridge between fully and direct map. And that's the story of what we call a set associative, which we kind of create a fully associative among each direct map cache. Okay, so essentially we call these sets. Okay, each row in the cache, we call it a set. So what used to be one element per set now could be multiple element per set, and within those elements then we can have fully associativity. Within rows we have direct map, but within columns we have fully associativity. Okay, so we have a 2D array that rows are like elements within rows are fully associative. In other words, I can just sit wherever I want, but between rows then there is direct map. So I can, for example, say, these people can only sit in first row, these people can only sit in the second row, but you can sit any chair you want in that second row. Okay, so that's kind of the idea of what we call a set associative cache. Okay, so if you recall, this would be the DM, this would be the FA or fully associative. The set associative would look like something like this. That within this, so any of these four could be mapped into this set. Any of these four can be mapped into this set, but within the set, I can just put anything I want wherever I want. Okay. And then we call these ways. So when we say 8-way, which I just said for Boom Core, it means that I have 8 elements in this row. How many rows do I have? That depends on the size of the cache. So for example, when I say 32 kilobyte set associative, I need to know what's the size of each row, then divide that by this size, and then I'll have the number of rows. But within each row, I know that there are 8 elements. So I can put 8 different blocks of cache within one row. Okay. Typically, the number of ways are either 8 or 16. The reason for it is that beyond 16 is, again, makes things very complicated to search. Below 8, you will lose performance. So 8 or 16 is kind of like the sweet spot for set associative cache. Okay. How do we actually do the lookup? In order to get a very fast lookup, we usually do it in parallel, since we have 8-way or n-way set associative. And your line could be any of these 8 ways. I need to search all of them at the same time in order to get as much as speed possible. Okay, so this is what we usually say parallel lookup. So for example, I'm showing a 2-way because I have 2 different ways. I search the tag in both tag stores, and then if I find a match, then I'm going to say this is like what we call a cache hit. If I don't find a match, then I call it a cache miss. If I had 8-way set associative, then I had 8 of these tag stores, and I needed 8 of these comparators. And you can see that quickly things become very expensive. But I really need to do this search in parallel in order to achieve the performance. Otherwise, I would have done it serially. Like, I searched the first way, and then the second way, and the third way, and so on and so forth. Much slower than what I want, because searching takes a lot of time. And remember, cache needs to be very fast, which needs to be within 1 cycle or so. Okay, so things should be parallel, but the trade-off is the power and the area. Okay. So this is kind of like the idea of direct map, set associative, and fully associative. Essentially, direct map, you just quickly search just one particular area. Fully associative, you need to search everything. But set associative, you just search a few specific places. It's kind of like a nice bridge between the two designs. If you want to compare the cache design, this is the formula that we usually use. We call average access time, or AAT. So you can think about the average access time as combination of three different parameters. The hit time, as in the time it takes for us to find the data and bring the data back to the CPU, if the data is indeed there. But of course, cache cannot achieve 100% hit rate, right? If it could achieve 100% hit rate, then would have been an amazing board. But since we have limited space, we cannot. So if the data is not in the cache, then we are talking about the miss rate and miss penalty. Miss rate, of course, is the frequency at which we don't have the data in the cache. And miss penalty is the time it takes for our data to go and being fetched from the lower level of the cache. So for example, the miss penalty for L1 is the time it takes to bring the data either from L2 or L3 or DRAM. The miss penalty for L2 is the time it takes to bring the data from L3 or DRAM. So not every layer of a cache has the same miss penalty. Depending on the layer of the cache, you have a different numbers. Okay. So let's actually talk about this direct map. So we did this exercise in my class. So let's actually do it together here. So let's say we have a direct map, fully associative and set associative cache. Let's actually talk about these three metrics: the hit time, the miss rate, and miss penalty, and see which one is the best among each group. So for hit time, between direct map, fully associative, and set associative, which one do you think is the best?
Direct map.
Direct map, because it's just boom, you know the address, you can go and bring it. And then between set associative and fully associative, which one is better? Set associative, because it's small, it's a search, but it's a smaller search. Okay, so it's something like this, right? What about miss rate? Which one do you think performs better? Fully associative. Why?
High utilization.
High utilization. So better chance of having that. Then
Set associative.
Set associative, because again in between, and then of course direct. What about miss penalty?
Associated with the next layer of the cache, isn't it? It depends on.
Let's say they are the same. For all of them, it's the same layer. Which one is better?
Direct map. I don't roughly say, but direct map, you could figure out that you have a miss very fast.
But that's kind of embedded in the hit time. So the definition of miss penalty is the time after we figure out it's a miss. So yes, as someone says, it's the same, because miss penalty is not relevant to the current stage, it's about the lower stage. Okay, so we're gonna have something like this, that you will see that direct map doing a better job in hit time, doing a worse time in miss rate, and miss penalty is the same for all of them. As you can see, the SA is kind of like in the middle. So now give me this answer. If I want a really performant cache, like let's say L1, let's talk about L1 and L2. What do you think would be a good idea for L1? Should I design my L1 a direct map cache, a set associative cache, or a fully associative cache, and why? And if it depends on what? Let's talk about L1. What do you need in L1? You want very fast response. So do you think DM is a good option? Why not?
Wait, yes.
Okay.
Sorry, I was looking at my.
All right. So you think DM would be a good option for L1?
Right.
Okay. And Neil, do you want to say something?
Higher miss rate.
Say it again.
Higher miss rate.
Higher miss rate. So then what? Then we should do fully associative?
Yeah, the size is very small, so it will not matter much, right?
Okay, so you're saying that if we can do a compromise, so hit time is not that much. Okay. You want to say something?
I was also gonna say fully associated because you don't want to miss at all when you're at the L1.
But what if your data is coming back slow? So you don't miss at all, but your data is slow.
It depends.
It depends on what.
You have a direct map cache with a very bad miss penalty, then it's not worth it. Versus if you have a fully directed cache or fully associated cache with like 100% hit rate, then that's also pretty good. So you have to kind of determine what your weights
Okay.
are.
The miss rate penalty is much higher than the hit time penalty.
Okay.
So
Okay. So all you're saying is a good compromise to go with fully associative.
it's
Okay. Yeah.
Kind of add on to L1 is usually very small, so to search through all that. Place would be probably better compromise.
Okay. And then.
If you have a small fully associative cache and you have one comparator for every single line, then wouldn't that be like instant anyway?
Yes. So that's what we do actually, right? So we pay the, so all the things you said is correct. Essentially, what will happen is we really want the performance of FA in terms of miss rate, right? Like you want to minimize the miss rate, but we don't really like the hit time of it, okay? So what should we do? What we do is this, as I said, we do this parallel lookup. So we add more hardware to our system. We design very nice and very fast comparators such that the fully associative performance becomes the same as a direct map performance, okay? And now we have the good performance in terms of hit rate, okay? So we get a really good hit rate. But again, we cannot really have a gigantic fully associative. We cannot like have a 30 kilobyte fully associative cache because that means that I need thousands of comparators. What we do is like we do set associative, which gives you a little bit of fully associativeness, but it's not crazy amount of comparators, okay? So I kind of like, if I want to have a really performance, I'm going to add ways to my set associative, make it more fully associative, which means that I'm going to add more comparators and all to my system. But in that case, the benefit I get is the performance, the hit rate. And if I want to design a low power cache, what I would do is then I will just put it as a direct map because there I cannot afford to do the parallel lookup. So I put a direct map cache because the hit rate for L1 is very important to me. And as long as I can do other tricks to kind of utilize the cache and kind of distribute the lines, then I get the fast hit rate of a direct map without really adding lots of comparators. So like for low power cache, direct map is a better option. Okay. So that's kind of like the story of the design of a cache. There's lots of things that, you know, if you're interested, you can watch the lecture, the basic lecture that I have. But let's actually talk about a few other problems with the cache as well. The first is, what should we do when the cache is full? Okay, because regardless, I mean, for direct map is easy because you know the address, you kick it out. But for fully associative and set associative, you have options, right? So since they can sit whatever they want, you can also kick out whoever you want, right? So I need to come up with what we call a replacement policy in order to decide what should I kick out, right? So what should I replace my new data with? And this is the story of what we call different replacement policies. This is what we're going to actually talk a lot about next week. We're going to talk about, you know, advanced replacement policy strategies. In regular undergrad course, people usually talk about LRUs and pseudo LRUs and random and FIFO. We're going to talk about more advanced versions, and this is actually would be your second championship competition. We're going to design a replacement policy that beats the regular LRU replacement policy. Okay, so this we're going to talk about next week. But before jumping into, so in addition to talking about that, we also want to optimize these parameters, okay? So again, if you think about the cache performance as combination of hit time plus miss rate times miss penalty, we want to see how we can improve the cache by using this. Some of these things that we already discussed are for optimizing this, right? So let's actually talk about this a little bit more. So let's talk about the miss rate first, because that's the most important part of any cache. The first thing that we do is what we call increasing the block size, okay? So the idea is this, that what you can store in each line of the cache could be as small as 1 byte, okay? So for every column in this cache, you can just store 1 byte, okay? In the other extreme, you can store a large number. You can, like, let's say I can store 1 megabyte. So for one cache, I just store the entire 1 megabyte, or 1 gigabyte, whatever, like crazy number. Okay. So now the question is, how should I decide what is the block size that I need to store? Like, what is the right amount of storage for whatever we want to store in a cache? Okay. And what do you think the answer is? Like, what are the things that you need to consider for block size?
Latency, because the more you put in there, the longer it's gonna take.
Yes. So if you bring a lot, then two problems might happen. One is, if you're bringing a lot, you also have to kick out a lot. So in other words, what we call a pollution. You are polluting the cache, especially if your things that you're bringing are not that useful most of the time. Okay. The second is the amount of time that you need to put in order to bring things goes higher as you increase the block. So in other words, your miss penalty is increasing. So you need to kind of be careful. But what is the benefit? Like, what's the usefulness of increasing the block? Like, why would be a good idea to bring more?
Usually there's spatial locality.
Spatial locality, right? So the idea is that if I have some form of an array, if I bring index 1, it's a good idea to also bring index 2, 3, 4, 5, and so on and so forth. Why? Because if I'm accessing index 1, very likely I'm going to access these other indices in very near future. So if I bring it to the cache, the whole idea of the cache is bringing things closer to the CPU so that the load time is faster, right? So if I can bring things, if I anticipate and bring things faster, then I have performance, okay? So there is this constant battle between I should bring more, but I also don't want to bring more, okay? So this is kind of like, you need to find the sweet spot, okay? You need to find the best size of the block. And obviously, this is not just 1 byte, it's more than 1 byte. Usually, most of the caches use 64 byte as a cache line. This is usually the block size, but you can even go crazy and bringing that as well, okay? So essentially, this is, as I said, this is the idea of cache block. So when we say cache block, we mean like multiple bytes. We don't say 1 byte, okay? We load things at the block level in the cache instead of at the byte level. Although my memory is still byte addressable, so I can still read and write things in byte granularity. But when I'm bringing things to the cache, I bring it in the block fashion, okay? Yeah. And then how do we kind of extract a byte from a block? We use this block offset thing. So the size of the block, whatever it is, the size of the block offset should give us still the byte addressability, because again, we always need byte addressability in our designs. Yeah, so this is kind of like our cache address would look like. So it used to be just index and a tag. Now it's block offset, index, and a tag. Okay, so any address is block offset, index, and a tag, basically because now we are increasing the block. So for example, if our block are 2 bytes, then log of this would be the block offset, which means just 1 bit. If my block size is 64 bytes, then log of this would be the block offset. Okay, so that's what first thing you do, that you always set aside the block offset. The rest becomes the index and the tag in your system. Okay, so this is kind of like how with block offset your cache would look like. So in a direct map, you have, let's say, if you have 8 different blocks, then you need 3 bits for the block offset. So each one of these is 1 byte. Then, for example, if I have 8 different sets in 8 different rows, then I need another 3 bits to kind of like find the index. and the remaining becomes the tag. So for example, if my addresses are 32-bit, I have 3 bits here, 3 bits here. 32 minus 6, 26 remains is my tag. Okay, so this is how we're gonna like address this this direct map. Same story for fully associative and set associative. For fully associative, we don't need index since there is no notion of indexing. So still I'm gonna have my block offset the 3 bits, the rest becomes the tag. So in this case, 29 bits becomes the tag. And as you can see, we have parallel lookup for all the rows that I have in my cache. Okay. And then finally, if I have something like a two-way set associative, then again, I'm going to have 8 of these bytes. Then I'm going to have 4 different rows. In other words, 2 bits for indexing, and then remaining bits would be for the tag. Right? So this is how we're going to do a two-way set associative. Okay? Again, if you have questions, take a look at these and feel free to ask those questions on CampusFire. Okay? So as I said, the block size cannot be too big because bringing too many data has two problems: miss penalty and pollution. So if you actually look into the miss rate and block size, what you will see is that as you decrease, as you increase the block size, your miss rate decreases. At some point, it will be minimum, and after that, it goes back up because of the cache pollution. Because the more things that you're bringing, you are also kicking out other useful data that you would have used. So at some point, it's no longer beneficial to increase the block size. So keep that in mind. Okay. The second thing that you can do in order to fix the miss rate is that this is already what we discussed, that we increase the associativity. Fully associative is better than set associative, then better than the direct map, right? And again, the question that I asked was, how big should be my set associative cache? Like how many ways? And if you look at the size of the log size of the number of ways versus the miss rate, what you will see is that again, at some point, it's kind of flattens. That it doesn't matter how many more ways you're adding, your miss rate doesn't really go down. Okay, but the problem with this is that this is the optimal point, because beyond this point, you're adding more comparators, you're adding more delays and power to your system. So you want to stay this, and you don't want to go to this gray zone. Okay. The third thing that you can do to increase the miss rate, decrease the miss rate, is just having a bigger cache, right? So this is like very obvious. Larger cache, more data, happier we are. Okay. But unfortunately, there is a limit to the cache size as well. What is that limit? The larger the cache, the lower the hit time. The reason for this is that think about cache as this big load of capacitance. Okay, so every row, the way that we design our caches is that there's kind of this line that goes through all the cells, all the rows. As I add more rows, I'm increasing the load on my bit line. Okay, as I'm increasing the load on my bit line, I either need more current to drive this line, or I need more time to drive this line. Think about the capacitance of this line goes higher and higher. As a result, the time it takes for charging and discharging this line becomes higher. So you don't want a crazy big cache line for hit time purposes. That's why L1 is usually limited to 32 or 64 kilobytes. Otherwise, you cannot achieve the hit time of one cycle the way that we want, unless we can design better kind of sense amplifiers and all those things that we can't at the moment. Okay, so also don't think that, oh, if I just increase the size, I'm going to get the better performance, because first of all, you're going to again have diminishing returns. That not necessarily if you increase the size of the cache, you're going to get better performance. And second, your hit time increases, so there is not benefit of doing that. Okay. The fourth thing that you can do is what we call prefetching. Okay. The idea of the prefetching is that if I can anticipate what I need in future, I can bring it. I already told you that if I see an array that I see like I1, like A1 is being accessed, most likely 2 and 3 and 4 and 5 also going to get access. And we anticipate that by making the block size bigger. So we, instead of like bringing 1 byte, we're bringing more. And in other words, we are prefetching in that sense, okay? But as I told you, if I want to go really crazy with my block size, there are other issues. So what I can do is that I can create this logic to kind of see when is a good idea to bring more, and at that time I'm going to bring. So instead of doing some form of a static block size based approach, I can have a logic that kind of predict whether or not it's a good idea to bring more data. If the logic says I'm very confident that more data is helpful, only in that case I'm going to bring more data. Okay, this is what we call prefetching and prefetcher. Okay, so the prefetcher is essentially reducing this amount of misses that we're going to have. But if your prefetcher is doing a horrible job of predicting, it actually has a negative impact to your system as well. Okay, so it's very important to design a good prefetcher in your system. Okay, there are 4 different questions for a prefetcher, such as what addresses should be prefetched, when should we prefetch it, because if you anticipate and predict that you're going to need something, if you bring it too early, it's not useful. If you bring it too late, it's also not useful. So the timeliness of your prefetching is also very important. And then the question is, if I'm doing the prefetching, where should I put it? Should I put it in L1? Should I put it in L2? Should I put it in L3? What should I kick out? So there are a whole bunch of questions like this that I need to answer. And then finally, the question of the prefetcher is where that prefetcher should operate. Is it the hardware unit? Can I use it at the compile time? Can I use it at the software developing time? So what can I do? So there are a whole bunch of different designs for a prefetcher for doing all those things. And I'm not going to go through the prefetcher design in this class because we have lots of other things to discuss. But prefetcher is actually very powerful, similar to branch predictor. It's no longer kind of like being active, but in the past, it's like there were a whole bunch of works on the prefetching as well. Okay, there we have software prefetcher, hardware prefetchers. I'm going to skip this. An example of this, just you can see at the software level, is like something like this. That if I have something like this, like simple code as this, then I can essentially tell my hardware to prefetch because I know for a fact that I'm going to run through this iteration loop. So as a programmer, I can actually have macros or special instructions that tells where the next address is going to be and tell that to the hardware, and the hardware can prefetch it for me. Another interesting thing that we can do is that if I have something like a linked list, which is much more difficult to predict because essentially it can go anywhere, I can again tell it to provide some indication to the hardware designer that this is where the next address is, and the hardware can go and prefetch it. So there are tricks like this at the compile stage that one can use in order to improve the performance of the cache. Okay, and then you can do all these things in hardware the same way that we do branch predictor. We can have hardware prefetchers. We can see the pattern, and based on the pattern, decide what to do next. So all those stories that we talked about in the branch predictor kind of applies. Different set of logics, so it's not the same, but kind of the way of thinking is the same. We could have had a prefetcher championship, but that could be something that we can do next year, maybe. Anyway. All right. So as I said, prefetching is great for bringing good data. So if you have a good prefetcher, can do this accurately, then you're going to get performance. You're going to reduce your miss rate. Okay. Another thing that you can do to reduce the miss rate is what we call a victim cache. Okay. So here's the idea of a victim cache. Remember, I told you that the problem with direct map is that you're not utilizing your space that much because you have lots of conflict in one address. Like, one address comes, the next address is exactly mapped to the same address. As a result, this one is kicked out and this one goes in, and this one is kicked out and this one goes in, and so on and so forth. So it's kind of like a ping pong between a bunch of different addresses. Okay. So in order to fix this, what I can do is that I can add what we call a victim cache, a very tiny cache that sits between the two levels of cache, that once I start doing this ping-ponging thing, The one that's being kicked out, instead of being kicked out and being replaced in the lower level cache, is stored in this middle level victim cache. So that the good thing about this is that the next time that this kind of ping pong things comes, then the victim cache can provide that data very quickly. Okay. And if the victim cache is as fast as the original cache, then it's as if that we are kind of like, having the same performance as, like, we're kind of eliminating this ping ponging based kind of like, constant conflicting based approach. The question is, okay, how big should be this victim? And surprisingly, this victim needs to be very small, because the scenarios where there are lots of these conflicts are not very, common. It's very rare. Okay. So I need a very small cache that kind of absorb this kind of, conflicting behavior. Instead of like, putting it all the way to the next cache, I put it into victim cache. The victim cache provides it. Since it's small, it's very fast. So all the good things that we can have. And this way we can reduce this conflicting misses a lot. Okay. Of course, the downside is extra overhead, more complex design, because now I need to kind of manage the data between the victim and the lower cache and the higher cache. I need to make those decisions. So there's also these trade-offs that comes with it. All right. And then in addition to all these hardware techniques, there are a whole bunch of software techniques that one can use. For example, you can reorder your array accesses such that it kind of improve your spatial locality. You can reduce the number of branches. You can inline your codes and all those things. So anything that can improve the spatial locality of your design or improve the prefetcher performance could result in better cache behavior, could result in lower miss rate. Okay. So software developer can do a lot of things in order to improve the cache behavior too. Okay. Just keep that in mind. Like, for example, one example is the tiling. You can actually tile like row major or column major, and based on that, you can improve the design. Lastly, you can have a better replacement policy. We're going to talk about this next week when we're talking about this. Questions so far? All right, so let's actually quickly talk about reducing miss penalty and hit rate as well. So miss penalty is the time that the data is not in this cache, so we have to go and bring it from the previous cache. Okay, how do we do that? So we have different ways of improving this. So first of all, if you remember, the write buffers or load store queues was great for this because we can do the forwarding, right? So like remember that we had the load and we had the older store. If the address of this load was same as store, what we could do is that instead of going all the way to the cache and bring it, this store could forward it to the younger load. Okay, so this is actually the way that we can reduce the miss penalty, right? Because we are essentially accessing that buffer instead of accessing the cache. So that's how we can actually get a much better performance. Okay, but of course, again, the overhead would be area overhead and power overhead because of adding this. The second thing that we can do for miss penalty is what we call early restart. Okay, remember I told you that caches are in blocks, so there are multiple bytes within one cache. Okay, but let's imagine that the CPU wants a particular byte, or maybe like 4 specific bytes. It doesn't need the entire cache block. Okay, so what should we do? One thing we can do is that saying that, okay, I need to get all the data within the block before I forward the data to the CPU, okay? Although CPU only needs 1 byte and I'm reading 64 byte, I'm essentially saying that, oh, wait for 64 byte delay before I provide you the data. Alternatively, what I can do is I can forward the specific byte or set of byte as long as they arrive. I don't need to wait for the entire block to come. As long as those bytes comes, I will forward it to the CPU. This is what we call early restart. So essentially, we restart the processor as early as we receive the data. Okay, and then a minor optimization for this is what we call early restart with critical word first, which means that if the CPU wants somewhere in between The obvious problem is that I need to wait until then and then forward the data, okay? What I can do instead is first see what exactly CPU needs and first ask that from my lower memory, okay? So the critical word, I first ask that will come. I forward that to the CPU and I'll wait for the rest of the block to come, okay? This is what we call early restart with critical word first, okay? Questions so far? Good. All right. Another thing that we do in order to fix a miss penalty is adding more levels. Essentially, the whole idea of cache hierarchy is reducing miss penalty, if you think about it, right? So if you think about this is, we have, one level of cache, but the reason that we are adding level 2 and level 3 and level 4 sometimes is because of this kind of like gradually increasing the delay, okay? So that's why we have what we call a multi-level cache. So bigger but slower. But if we kind of like, have this hierarchy, then we can increase the cache performance. If you actually think about this formula, this was the formula that we talked about. Essentially, if you just think about L1, the hit time of L1, the miss rate of L1, and miss penalty of L1, okay? But if I have multiple level caches, okay, what will happen is that this miss penalty itself becomes another AAT for the next level. So it becomes AAT of level 2. And if I have some hits in level 2, then I actually reduce this miss penalty, okay? I'm not gonna like drive the formula for you, but you can probably do that yourself. But the general idea is that if I add more layers to my cache, then I'm effectively reducing my miss penalty. Because instead of going every time all the way to the DRAM, I sometimes go to L2 and then go to the DRAM. So that's how I'm gonna increase my performance. Another thing that we do with reducing miss penalty is sub-blocking. Remember again that the problem with blocking was if I increase the block size, right, it takes more time for data to come back, okay? So I can increase the block by doing this idea of what we call sub-blocking, which essentially we say that, you know what, we don't need to bring all the data all the time. We just bring some of the blocks whenever we want. And if we decide we need all of it, we bring all of it. How do we kind of like decide what to bring and what not to bring? We need to kind of like increase our tag the valid bits to kind of tell them whether these blocks are valid or not, okay? So think about this as our regular block. Think about this as our super block. And then this valid bits basically tells whether we have those sub blocks or not, okay? This way I can have the kind of somewhere between having big blocks but not having big miss penalties, okay? Again, the issue with this would be more complex circuitry. I need more storage for the sub blocks. But on the other hand, I enjoy a better miss rate and a lower miss penalty. And finally, how do we reduce miss hit time? We already discussed this. If you have something like a direct map, much faster, right? Generally, smaller caches, the better the hit rate is. Hit time is. The second thing that we also discussed is parallel lookup. So if you can actually look up both all the ways at the same time, we improve the hit time. And lastly, as I said before, another way to improve hit time is speculative loads. We talked about that today as well. That instead of waiting for the store to finish, we issue the load, and then the load would be faster. And then especially if the load is in L1, then we get a faster response. So in other words, we are improving our hit time, okay? So this is kind of the summary of all these things that I said. For miss rate, we have improving the block size, associativity, size, prefetching, victim cache, compiler, replacement policy. For miss penalty, we have write buffer, early restart with critical word first, adding more levels and sub-blocking. And for hit time, we have set associative cache, adding more levels, parallel lookup, and speculative load, okay? So these are kind of like the techniques that we use in order to improve. If you have questions about caches, watch, lecture 12 and 13 of my undergrad class. Otherwise, if you feel good about it, next week we're going to talk more about replacement policies and multi-cache systems and so on and so forth. All right. Thank you.